Okay, so welcome everyone. Thank you for attending this talk on user-controlled privacy, taint, track, and control. This is joint work with David Basin and Sergeant Kristich, the three of us from ETH Zurich. So when you look at the state of data protection today in the wild online, there's basically one thing that's really striking. On one side, you have a lot of fines being imposed on companies that are not compliant. I think right now we're at like 4.5 billion for GDPR alone. On the other side, you also see a very, very high level of non-compliance. And my colleague Karel, who stands here in the crowd, with colleagues showed a couple of years ago that about 90%, more than 90% of websites were non-compliant, looking here only at cookies. So there's a huge divide between these two things. What we can do to improve over this situation is try to follow guidelines like those of privacy by design, so try to build systems that are correct by construction. And in particular, this is not just one option. This is actually something the GDPR, among others, mandates us to do. So in this paper, we're going to focus on one aspect, which is consent and purpose-based usage, which is at the core of the GDPR. And we're going to look at how to enforce relatively complex policies like the one I'm going to show now. So suppose we have a user, Alice, that is working using an application like Twitter, a microblogging application, and she requires that for any tweet she posts, no data derived from that tweet is ever used for marketing purposes, that for analytics purposes, such data can be sent only to a trusted third party, and that 1 week after she posts the tweet, data derived from it can only be used for service purposes, maybe because she doesn't want to look at the statistics later on. Well, this looks like a relatively complex policy. Actually, this is not supported by most previous works. And in this work, we're going to show how we can actually enforce such policies that are controlling the tracking, so tracking data through systems, so also working on derived data, and that support restrictions that are user-specified, so users can give consent and revoke it, that are per input, so different inputs have different restrictions, and that also time-dependent, and that restrictions can change over time. Okay, our approach is called taint, track, and control. I'm going to show you here an example how that works. So we start with a user U that wants to communicate with some applications here, and that would typically, in order to do that, generate some input. So let's look at this personal data here that is going to flow into the system, represented here the value by this small half circle. So this input is going to go into the system, and it's going to be captured by a wrapper, which is controlling the inputs and outputs of applications. So the information here is going into the wrapper, and what the wrapper is doing in our system, it's the taint phase. It is actually adding a unique identifier to this input, which we call a unique taint here. And the unique taint is going to be attached to stick to this input value. It's also generating an input event that we're going to send to a so-called monitor. The monitor is going to look at events generated by the system and tell the system whether to perform some actions to make sure compliance is there at all times. The monitor also has access to the user's policy, so preferences in terms of data usage. Here, for input, there's not much to do because inputs cannot be blocked by the system, so we simply register this input event. Now what is going to happen is the data is going to go into the application, which is controlled by the wrapper, has a special execution environment. It's the track phase, and we're going to track the data flow through the application. So suppose maybe the application wants to duplicate this data, wants to store it into the database. Here all the taints always persisted, and now read some other data from the database. So some other data is there, enters the application, and maybe we do some operations. We combine these two inputs, make a new output out of them, and all the taints are always propagated, so we just accumulate them. Suppose this is now the output of the application. It goes through the wrapper to be output to the user, and what we're going to do is we're going to enter the control phase, in which we are generating events corresponding to the output, encoding which input have influenced the output, so we have data traceability, sending that to the monitor that can register these new events, say whether it's fine or not fine to output the corresponding thing. Here, let's say the output is accepted by the monitor. We get this verdict, and we can output our result to the user. Okay, so in a nutshell, that's how the approach works. So we have two phases here, the taint and control phases that are based on something called runtime enforcement, which is from the formal verification community, where we generate events corresponding here to inputs, outputs, and interference between inputs and outputs that register things like the purpose of processing and which user you're sending data to. And we're using a backend also from our group, ANF-Poly, that supports a very expressive language called AMFODL. And we can write a policy you've seen at the beginning in this language. I mean, you don't need to understand this. This is just to show you we can actually do it. We can write these complex policies. Okay, and in the track phase, we're using another technique from formal methods, dynamic information flow control, where we are proposing in our paper a new programming language based on a fragment of Python that propagates these unique taints. So the inputs are marked with a single unique taint, and data in memory or database are marked with sets of UTs that are propagated. And our system also supports introspection, meaning you can check ahead of time whether some output will be allowed or not. Okay, how that works behind the hood, I'm going to show that on a very simple example. Suppose you have a small program that reads some inputs and tries to combine them. What we're doing is we have value and UTs attached, so unique taints attached to values in memory, and we also have the program counter, so how we're going in the execution, and corresponding taints in our memory model. So when we're reading some inputs here, this is going to, add some values in memory, but also add some unique taints taken from the user here. And we're proceeding through the code, say we want to check on x whether it's equal to some constant. What we're going to do is the control flow is going to change. We're going to enter the if, so we need to load the taints of x here into the program counter taints. And now we're executing our assignment. Here r equals to y plus z. And what that does is that combines the values of y and z and also combines all the taints. So we get the taints from x and y, but also the taints from y and z, but also the taints from x, because x influenced the control flow, and hence it also influenced the content of the variable r. Okay, so that's how we, in a nutshell, track data, and then we are leaving here this if block so we can remove the taints from the program counter, just proceed to whatever we have to execute next. In our paper, we present formal guarantees and proofs for what I just showed you in the full setup. So we model online applications as labeled transition systems. We formalize interference between inputs and outputs in our system. We provide formal semantics for this core of this Python TTC language that we present, which is the language in which we can write applications in our system. And we provide the semantics of the full system that combines both these programs, the wrapper, the monitor, and all of the bookkeeping activity in the system. And using Isabelle Hall, which is a theorem prover, we prove that if the monitor in our system is loading with a policy that fulfills certain conditions, see paper for details, then any code running in our system always complies with the policy, which is exactly saying that you have privacy by design for this set of policies that we support. We also have an artifact, an empirical evaluation. We have the artifact reproduce badge for our work, the prototype web programming framework built around this Python CCC, which we call WebTTC, is available there, so you can deploy your own small applications. We have 3 proof of concept applications that we have deployed, one conference management system, microblogging, and health record manager, all of them coming from previous work. And we also have the fully mechanized formalization and proofs in Isabelle Hall, which is about 5,000 lines of code. We have evaluated our work by successfully porting several proof-of-concept applications from previous work, and we showed an enforcement overhead of about 1.5 to 2 times over the pure Flask application without any security, provided that we introduce some features such as appropriate pagination in code, which is common sense. We showed performance to be comparable or better than previous works in a similar field, not working with these complex policies, but with some previous simpler policies, such as Jacqueline. And overall, we showed that the approach is applicable and usable in real systems. So such as for applications and future work, we also already published a follow-up to this study at Azorix last year, where we applied WebTTC to enforce about 10 GDPR requirements, showed in a slightly more complex setup that we could do such thing as a data erasure, for example, using our unique taints to track data throughout the system. And we also are currently working on a number of extensions. These include optimizing tracking, using static analysis, using TTC in distributed systems, and anonymization and declassification. On that, I would like to thank you for your attention. If you're interested in this work, you can feel free to drop us an email. We'll also be at the poster session tomorrow afternoon, and I'm happy to take your question now.
Any questions? Okay.
Yes.
Thank you very much for the presentation. So I would be curious, how expressive is this, how capable is this Python TTC in case of, can I just take my Python code, run it, or what will I have to do? Is it going to restrict me that I cannot use certain aspects of it? And you also said that you proven the core of it. What does this core mean in some simple way? Explain.
Yeah, thanks. So that's a very good question. So typically, I'm going to answer a second question first. In general, when we're talking about core languages here, it's common to many papers in this kind of field when you're doing IFC in general. Addressing all of the features of the language at the same time is very hard because there's aliasing, there's dynamic memory management, there's a lot of things in the language. So usually you take a core of it. In our case, it's an imperative core, so it's something like loops and ifs and some control flow and simply like key value pairs as memory models. It's very common also in, let's say, functional programming that you take lambda calculus, so you take some kind of model of the language and you do the semantics and proofs on them because it allows you to simplify it. Otherwise that would have taken, way more than 5K lines of code to prove. So that's the first thing. Then on the applicability or the restrictions this imposes. So we've worked on a fragment of Python. We're not supporting whole of Python because we basically have to rewrite Python code to propagate these taints. So this is a bit expensive in terms of of engineering. Of course, if you would have if you want to create a startup that works on this, I guess you can cover much more field with much more space than we're doing as researchers because we just want to get the application to work. So for now, it's a bit restricted. We are currently also working on extensions where we're trying to isolate the part where we actually need to propagate taints, such that, for example, we can use any arbitrary library in the backend by simply putting the taints when we're calling or removing the taints before we call the library, and then adding back the taints when we retrieve the result from the library call. This is not something we've been focusing on so far because the goal was to show that the concept works, that applications can be written. But so far we are supporting a small fragment of Python that also has a standard web framework features such as writing to an SQL database, setting session variables, setting cookies, that kind of things.
We could take one more question.
Hi, so I was wondering about the extension for the distributed systems. Are you, just kind of like a follow-up to that question, is are you looking at polyglot settings where you have different languages, or is this more of a microservices setting where you have lots of different components and you're trying to kind of isolate where you're doing the taint propagation to simplify things?
An excellent question, thanks. We're looking at currently. We're looking at it first. We're looking at it first from a formal perspective. So, why does it take you at a logical level to do that? And there's a number of challenges there, typically because information going to flow from A to B. So that means that your taints also have to flow. But then if they flow before you're doing the call, if the call is conditional, then you've already leaked data. So there's a lot of interesting logical, technical questions that have to be sorted out before we even think about languages. What we're trying to focus on in terms of applications is microservices on one side, because this is a very common use case, but also you can think about simply client to server code interaction. Because this is also in a nutshell, at a logical level, this is the same problem. You have different pieces of code that interact with each other. So I would say the answer is at the purely logical level, we're looking at it globally without any language specific context, but when we're going to implement it, it's probably going to be Python first because that's what we've worked with, and then we can simulate these different cases that we're talking about because you can have server, client, and Python. You can also have microservices. So that would be the first thing we would try out.
Okay, thank you very much. So that's the end of the Q&A for this paper, and thank you again for the talk.
Okay.
Okay.